So welcome. So I start thanking the organizer for having me here. So and it's a great opportunity that I can share something with you, and also the ICTS for this wonderful campus, of which I'm really enjoying. So today I'll be talking about a particular cosmological scenario where at the end of inflation, the universe is going to be dominated by the oscillations of the weakly coupled scalar field, which is called the moduli. And in that particular kind of scenario, how the moduli masses are related to the inflationary observables. So that's the goal of the talk. So this talk is based on following references, which I did with my student Kumar, Anshuman Moharana in HRI, and Mikhail Chicoli, and Fernando Quevedo. So what is the take-home message, okay, for the whole talk? Now the main point is that the number of e-folds during inflation, that is from the end of inflation to the time when the cosmological scales went outside of the horizon, that number of e-folds crucially depends not only what is happening during inflation, but it also depends what is happening at the end of inflation, that is the post-inflationary epoch, okay? And I will argue that in many of the supersymmetric and string theory motivated models, so at the end of inflation, the universe might be dominated by the coherent oscillations of the scalar field. So this can effectively work as a matter-dominated epoch. And in that case, the number of e-folds is going to be reduced. And in that case, also the inflationary predictions are going to be affected. Okay? So that's the take-home message. So we shall try to argue. So this is the two the plots, the CMB, the temperature. This is the temperature plot, and this is the polarization plot. So before this has been discussed yesterday in the inflation talk quite in detail, but I'll try to argue in a bit of more from the observational point of view that how the matter-dominated epoch at the end of inflation is absolutely fine with observation. Okay, so once we take the temperature, we can do the two-point correlation analysis, and that we can do it by making plots for both the TT correlation, also the EE correlation, which is related to the polarization, and also the cross correlations of TE. Okay, where the x-axis for all the plots corresponds to a particular length scale that you see in the sky, each point in the x-axis. Okay, so that means, for example, this corresponds to a certain length scale which has this RMS amplitude of this large. So that's what roughly means. But what is important to understand that all these plots has this beautiful, nice peak structure, which is not easy to get it's not in a very standard cosmological scenario. Now, if you extract the data, extract the points from the data, what you get these dots. Okay, and then you have a beautiful theory of this strongly coupled plasma before the CMB was formed. And at that point of time, if somebody gives you primordial fluctuations of this particular form, and then you just evolve the primordial fluctuations with the transfer function, which depends on the late time cosmological parameters, that is the baryon density, dark matter density, and the cosmological constant, and all the details, you can calculate what is the value of CL. Okay, that you can do it in your computer. Once you do that, you just fit it with the data, which is this red line for all these three things. Okay, so given these quantities, that is the primordial fluctuations and these numbers, okay, everything fits with the data. That's absolutely fine. So that typically closes the so-called the 6-parameter lambda CDM cosmology. But what is missing, what is important to appreciate in this whole model is the issue about the coherent phase. What is important to understand that in this plot, at each length scale, there is a particular value of L correspond to the sum of the wavelengths, sum of the fluctuations, okay, from all different directions, okay, so each point. And unless those fluctuations are in proper phase, what is going to happen? You are not going to get a peak structure as like here or here. You are just going to get random addition, and therefore the peak structure is completely going to wash out. Okay, but this from the TT correlation, the peak structure happens only at the sub-horizon scale. So therefore, you can still think of agnostically that it can happen with some local physics. But this has been completely ruled out with the observations of the cross correlations that you see for TE. Okay? So temperature and the E mode polarization, if you just calculate the cross correlations with the random phase of the fluctuations that is phi, this DLTE should be 0. Okay? But what we see from the observation, that is, let's say L equal to 130, which is the super Hubble scale at the time of the CMB formation, this is not equal to 0. So that uniquely kind of tells us, okay, that at the time of CMB formation, there were super Hubble modes are existing, which they were coherently added. Okay, so this is coming out purely from the data. So therefore, looking at the data only, the only information that we have, okay, is that the fact that at the time of the BBN, the universe was radiation dominated. That we know from the very Coleman-Turner cosmology. And then we know that if this type of fluctuations is given to you as an initial condition, that fits the data well. But the important point is that if this fluctuations is given to you with a random phase, this is not going to fit the data well. So you need some coherent super Hubble perturbations. Okay? And also, from the late time cosmology, you need something like dark matter for the gravitational collapse to happen. And these coherent super Hubble perturbations are uniquely, I would say very generically produced by the mechanism of inflation, because as it was discussed yesterday's lecture, during the time of inflation, what is happening, the cosmological modes are going outside of the horizon. Okay? Now, once they're coming in, okay, each particular wavelength, each particular fluctuations are coming in at same time. So therefore, all of them are coming in phase. Okay? So they're getting added in phase. Okay? And in addition to that, the issue about the super Hubble perturbations, obviously the inflation solves the problem that has been discussed yesterday in John's talk, both the horizon problem and the flatness problem. Okay, so this is one point which has not been discussed much, so therefore I wanted to emphasize that one of the very novel properties about the inflation is this coherent super Hubble perturbations. So agnostically, if I think about the history of the cosmology, history of our universe, what is absolutely fine from the observational point of view is the following picture. Okay, in the standard picture, what happens that at the end of inflation, the inflaton decays, it produces radiation, and it goes all the way to this epoch, and at this time, the universe becomes matter dominated. Okay? But what might happen, and which is consistent to the data, is that at the end of inflation, the inflaton decays, and it produces some radiation dominated epoch, but immediately, some oscillations of the other scalar field, which is not inflaton, can dominate the energy density of the universe, and it can decay much later. Okay? But it must decay before BBN to have the success of all the BBN that we know. And then after the BBN, the standard history of the universe follows. So in this picture, this alternative history of the universe, we'll try to correlate how the mass of the scalar field oscillations is related to the inflationary observables. And we will see, as I tried to mention in the beginning, the crucial point is that the number of E-folds are going to be changed. So therefore, this is the outline. So I'll talk about initially how the cosmology of the moduli works out. So this is a picture which is there from the late 80s. So how the relation between the cosmological mass and the inflation works out and some of the implications. And at the end, I'll talk about one concrete example in the context of the Kahler modular inflation, where the form of the potential has been calculated explicitly by some other group in the context of string theory. We just take the scenario and calculate how the observable changes. So what is the framework? The framework is the following. This is my moduli, which is given by the curly phi. At the time of inflation, this moduli field has a large mass, okay, and it is sitting at its minima, okay, which is a different position from its post-inflationary minima. Okay, so at the end of inflation, what is happening? The vacuum energy goes away, and the form of the modulus potential is changing, and the field at the end of inflation is making oscillations from this point to this point, and then keep on oscillating around phi equal to 0. Okay, so initially at the end of inflation, field has this large amplitude phi hat, which I'll argue later is the order of the M Planck. Okay, and these oscillations, the oscillations around this phi equal to 0 is going to dominate the energy density of the universe very quickly. Okay, the speciality about this modulus field is that we know for the modulus field what is the coupling. Okay, so therefore, this phi field can in principle be any field, okay, as long as it decays very late, okay, but we will be focusing on the modulus field, but at the very end, I'll mention some of the other words. So let's look at the inflationary observables that we care about. So this was discussed yesterday. The inflationary observables are tensor to scalar ratio, which is related to the height of the potential that is driving inflaton. Okay, this phi field. And then we have this primordial tilt, which is related to the slope of the potential when the cosmological modes are going outside of the horizon. Okay, so these are the roughly two observables we care, and we are going to understand how these observables are going to change. Where we stand at the moment? Where you stand is this is the tensor to scalar ratio that was discussed yesterday, and this is the energy scale of inflation. Okay, so this you can easily write down the scale of inflation in terms of the tensor to scalar ratio. So this is roughly the optimistic number, or maybe one order of magnitude smaller that we can detect. But the main point is that even if R is measured at the order of 10 to the minus 3, this V is not going to be reduced largely. Okay, so therefore, as you can see, even in the ideal case when R goes to 10 to the minus 4, the scale of inflation, the energy scale of inflation is just 10 to the 15. So therefore, to see tensor modes, some way you need some luck. Okay, because for example, if some way the scale of inflation is 10 to the 14 GeV, it would be very difficult to observe. Okay. On the other hand, the other observable, the prospect for measuring the other observable in a much more precise manner is NS is very, very promising. Okay, so I just quote some of the results, that is the proposed future satellites. For example, Core, Lightbird, and this is CMB stage 4, where this green contours, and here also this blue contour, are the present Planck sensitivity for the NS. Okay. Now, in the future, for example, this blue line, okay, which is for the core, the NS is going to be measured with the sensitivity of 10 to the minus 3, and that is irrespective of whatever the value of R, the fiducial value. Okay, so therefore, let's say, for example, tomorrow Stravinsky model or any of the model that was discussed yesterday, okay, is kind of validated. But at the same time, it also has to satisfy at the level of 10 to the minus 3, the spectral index constant. And these observations of the spectral index is going to be very crucial for the arguments that I'm going to put forward. So let's look at the thermal history of the universe. So okay, this is the standard history of the universe. So what is happening? So for the standard history of the universe, this is the time when inflation is happening. This is the log of the co-moving Hubble scale. This is going down. At the end of inflation, reheating is happening, then the usual radiation and the matter domination. And during the time of inflation, the cosmological scale, which I plotted in the terms of the co-moving scale, goes outside of the horizon when the value of the potential is Vk. The value of the inflationary potential is Vk. Important point is that those modes are again coming inside the horizon when the universe is matter dominated. Okay, so this incoming of the different modes are happening in phase for inflation. That's very, very crucial. And during the time of inflation, the exponential expansions of the scale factor is parameterized by this number of E-folds that I was mentioning at the very beginning. Okay, so these scales goes outside and comes back here. But the important point is that this potential energy Vk, okay, that is the potential energy when the cosmological CMB modes going outside of the horizon has to be evolved properly to the present energy density of the universe. Okay, and that once you know how these scale factors has evolved, okay, during the time of inflation or the reheating and the radiation domination, the fact this energy conservation that the Vk has to be evolved to this energy density, which is the present energy density of the universe, which you know with a very high accuracy, you can write down the following consistency condition, which has been quoted in all cosmology book, where n inflation is what I have been told in the last slide as nk, the number of E-folds during inflation. Now, let's look at it a bit carefully. Here I see there are two numbers, two expressions, which depends on the inflationary details. This 55 is a number related to some of the parameter goes like the present Hubble constant and so on and so forth. And then there is a one number which is here, which is related to what is happening at the end of inflation. Okay, how the inflaton is going to reheat to the standard model degrees of freedom, that is WRH and the NRH. How long is the reheating is happening? Obviously, we have uncertainties about these numbers. We do not know a priori what inflation model, how is the reheating is happening. So therefore, we kind of roughly give a plus minus 5 number here, and we make a theoretical prior. Okay, we make a theoretical prior that the N inflation is 50 or 60. Okay, so what we do as a cosmological, when you do inflation, we pick our favorite model, let's say half m square chi square. We calculate ns and r, those two observables, as a functions of nk. And nk, theoretically, we understand it is 50, roughly it should be 50 and 60. So we calculate ns at 60 and ns as 50. So for r, and then we plug it in the formula. We plug it in this plot, and this is the way this plot is generated. So therefore, these contours are purely coming from the observational data. And as you can see, these big blobs is for n star equal to 60, and this is for n star equal to 50. This 50-60 is the variation because of our uncertainty to know the details about the post-inflationary history of the universe. Okay? Better we know the post-inflationary history of the universe, this number is going to pin down with a much more accurately. Okay? Now the question is that how does making predictions change for the modular cosmology? Okay? Now this is the standard way we do it. Now in the case of modular cosmology, when the history of the universe is dominated by these oscillations, how this picture for this n star is going to change. So before I go into the details, so let's talk about what is the moduli. I mean, just to kind of introduce. So moduli are the light scalar fields. The important point is that they are Planck suppressed interactions. So therefore, they doesn't want to decay very quickly unless they are very, very heavy. Okay. At tree level, this modulus field typically has flat directions. Okay, it just doesn't have any mass. So therefore, you need to give those fields mass because you need to give those fields some wave. Okay. Now, so you want to make this phenomenologically viable because without a wave, it would be very difficult because the field is just always going to roll around. And this is the whole story about the huge industry in the string theory, how to stabilize the modulus, the SKKLT stabilization mechanism, large volume stabilization mechanism, and everything. How to make the modulus heavy. So you can take a very conservative approach that you make the modulus stabilize during inflation and make the mass of the modulus so heavy that it completely decouples from the inflationary spectrum. Okay? And then you just completely forget about it. But that is something, in principle, you can do it, and in some cases, people do it, and it happens. But it's not that always happens. Okay? What happens in many cases, as I'll argue later, that at the end of inflation, some scalar field, some of the modulus fields remains parametrically light. Okay? So therefore, they starts to oscillate at the end of inflation. Okay? And that field essentially is the field that I'm talking about, this phi. So let's look at a kind of representative Lagrangian of a modulus field. This has a mass, half m square phi square. This mass is the post-inflationary mass. But during inflation, this field also gets a mass because of the supersymmetry breaking. In the next slide I'll explain. It also gets a mass induced by the Hubble scale. So this is a large mass. So therefore, during inflation, the potential is dominated, modulus potential is dominated only by this term. You can actually forget about it. And during inflation, the field is shifted here because the potential is shifted by this amount phi hat. At the end of inflation, this h becomes 0. Okay, so therefore this term completely drops out. The field essentially moves from this to this point. And then the classical oscillation starts to happen. Typically, this y becomes order 1. Okay? Now, how do you argue that's the case? In the context of the supergravity, this is very much typical case, I would say. Because in the context of supergravity, the potential V is given by this following formula, where you have this exponential of K, where K is the Kahler potential, which was discussed yesterday quite a lot. For a typical value, a typical K, let's say canonical K, you can easily write down the form of the potential in this fashion. Okay, you just take it out the h square factor, and therefore you can see the V double prime is going to be proportional to the Hubble constant. Okay, this is the typical so-called eta problem that we face always in constructing any inflation model. So unless this direction is protected in some way or the other, typically this field is going to have mass of the order of Hubble square. Okay? And as you can see in these functions inside, there is no other scale other than the Planck mass. So therefore, anything that you write down typically is going to be the order of the Planck scale unless things are very finely tuned. So that's why the number y is going to be order 1, but you need explicit calculations to show that this number is order 1. Which I'll do it at the very end for one particular example. So a toy example, this is just a toy example, where you can see this is this Hubble-induced mass, this is the M3½ related to the mass at the low energy SUSY breaking. This term can be generated from the higher order superpotential term, and you can easily convince yourself that the phi hat is the order of A over B multiplied by M Planck. So unless this A and B are highly fine-tuned, this number is going to be order 1. Okay? This number can be also order 1 if you have a stabilization mechanism during inflation and after inflation, which are different. But as we know, this field must decay before BBN. Okay? So therefore, that puts a bound. So this is a very old result. The field must decay before BBN because we know that the BBN happened with the radiation dominated epoch, and that puts a bound that the mass of the modulus has to be greater than 30 TeV. Okay? And the gamma, that is the decay width for the modulus field, is given by very generically this m phi cube divided by m Planck square. So that's what you see. This is a very weakly coupled because it is suppressed by the Planck mass. So therefore, in this modified history of the universe, what is happening? You have the standard history, inflation, then inflaton decays, it produces small reheating epoch, produces the radiation when it thermalizes. But then, after the radiation thermalization happens, then the modulus starts to dominate. Okay, then this is the extra epoch that happens, and then at some point modulus decays before BBN. And then from BBN, the history of the universe goes as we know. In this case, if you just calculate the same consistency condition that I just described before for the standard history of the universe, what you get is the following formula. You get 2 extra term, which is related to the n mod divided by 4, and this extra factor. As you can see, these 2 terms, okay, more you know about the particle physics, that means how the modulus is coupled to the other fields, you know much more details about these 2 terms. Okay? But even if you do not know how do I interpret these 2 terms, the easiest way to interpret these 2 terms is the following. Once I know the gamma modulus, okay, I can calculate, okay, just by little algebra, what is going to be the number of E-folds contributed by the modulus field. And that depends only on the initial amplitude y and the mass of the modulus field. So I plug it here in the formula, and here all the terms are depending on the post-inflationary details, and here all the terms depends on the inflationary details. Okay, so I just repeat, this is an equality that has to be satisfied, okay, for any model as long as you know all the details here. Okay, you just have to calculate all the terms, that's all. But this must be satisfied just because of the energy conservation, nothing else. So the first implication is the following. The n inflation that was initially 55 plus minus 5 has a shift because of this extra term that appeared here. So you just now shift this term from left hand side to the right hand side, and this n inflation is going to be shifted by this number. So you plug some representative number for the mass of the modulus of 10 to the 3 TeV, the n inflation is going to be shifted to 40 to 50. So now, what does it mean? If the universe is dominated by a scalar field oscillations of 10 to the 3 TeV, the observable has to be calculated not at 50 and 60, but you have to calculate at 41 and 51. Okay? And therefore, the shift in the spectral index, as we will see, is going to be substantial, at least for the future observations. Similarly, for 10 to the 6 TeV, it is going to be 43 and 53 for all these calculations. I assume y equal to 0.1, which is from the effective field theory point of view, is within control. So what is the easiest way to understand that how this number of E-fold goes down? This is a simple cartoon. So this is an inflation that is happening, and the green line is our standard thermal history of the universe. Okay? And standard thermal history of the universe crosses this line, this log A0 at this point. Any history of the universe that you change, you must make sure that you have the same point here, because this point has been measured with a very high accuracy. Now, if you add this extra blue line, which is this extra matter-dominated epoch, only way you can match this boundary condition if you reduce this blue line during the time of inflation. So that's the reason 50 and 60 becomes 40 and 50 for the case of 10 to the 3 TeV modulus. Okay, and as you can see, if you keep it for the red, if you keep the number of E-folds the same, you will have a completely wrong history of the universe. So very quickly, So you can take the representative models, such as calculate how the observable changes. Then you can see for 10 to the 3 TeV masses how these observable numbers are changing from this point to this point. Now this is within the 2 sigma limits, okay, for these particular models. Definitely m square phi square models essentially goes outside of the horizon, outside of this 2 sigma contour. But for these models, they remains within the 2 sigma contour. But the crucial point is that this is the number that is going to be measured with this accuracy. This ns value is going to be measured with this accuracy. So therefore, any future observations are going to be sensitive to the shift. So that essentially signifies that how crucially we need to understand what is going to happen not only during inflation, but also after inflation. So as I tried to argue, that what are the implications? In many cases of the modulus dominated cases, the modulus mass are related to the SUSY breaking, and then in that case, you can try to relate the number of the SUSY breaking scale to this modulus mass. And in all the cases, the main point is the number of E-folds shifts to some other values with a central value of 45. And you can show very easily any mass, any scalar field mass which is less than 10 to the 10 GeV has to be taken care because the effects are appreciable. Okay, for the future prospects of the observations. You can take the same consistency condition in a completely different way. Now, you just look at these expressions. Obviously, we do not know much about these two expressions unless we know the couplings of the modulus to the standard model degrees of freedom. But what we know for sure that these two numbers are positive definite, because W reheating for the case of the modulus decays and also for the inflaton decays typically is always going to be less than 1/3 both from the theoretical understanding and from the numerical simulations. If these two numbers are positive definite, that means immediately these relations can be translated to an lower bound for the mass for the modulus, okay, which depends on the y. As I see, obviously for y goes to 0, this number should be 0 because there shouldn't be any bound. And then it exponentially depends on the number of efforts nk and the inflationary details. Okay, as we see here, the dependents are definitely correlated for sure, because these numbers cannot be independent for an inflation model. You have to calculate explicitly these numbers. Larger the value of nk for a particular model, stronger the bound, because this is a minus sign, then it becomes a plus. And smaller the value of r here, also the bound becomes stronger. And then the bounds definitely depends to a certain extent in the logarithmic way to the nature of the inflationary potential in this rho k divided by rho n. So we have rough idea what kind of models that inflation we work with. So there are one category of models where we just call it small field inflation model. And in that case, you can make it much more concrete. So you can take a conservative estimate of r equal to 0.01. As I said, if r is much smaller, the bound is going to be much stronger. And we know that for the typically small field inflation model, the potential is plateau-like. So therefore, you can actually also drop this number. And in that case, if you just plug the number y equal to 0.01 and for n equal to 50, which is a rough number also for Sarbanes inflation, the mass for this modulus has to be greater than 10 to the 6 TeV, which is definitely stronger than the BBN bound. This is definitely coupled with an inflaton sector and the modulus sector, whereas BBN bound is completely independent. So it turns out, if you just plot it as a functions of nk and r, the r dependence is very weak. Only crucial dependent comes from this nk. For any value of n greater than 44, the bound is always going to be stronger than the BBN bound, which is the order of few TeV, like 30 or 100 TeV. For the large field inflation model, what you can do, you can calculate all the numbers in terms of this parameter alpha, because large field inflation model typically are parameterized by these monomials. Okay, some chi to the power alpha, where chi is my inflaton. And you can just calculate everything in terms of this alpha. The crucial dependent comes from this factor. That is the factor that is 1 minus ns. That itself shows that ns, small variations of ns is going to give a large number here, and that's going to give you large changes in this m5. And it turns out, which is consistent with the previous plot, that for alpha equal to 2, you will see the mass of this m5 has to be much larger than 10 to the 10 TeV, which is excluded. Okay? And for alpha equal to 2/3, the bound is going to be insignificant. That means it is going to be less than few TeV. Okay? Now the point is that what to calculate now? I mean, at the moment, the point is that, as I tried to argue here, Okay, so let me just go this. Yes. Okay. So at the moment, if we know about more details about these terms, okay, we can actually extract much more information about from this quantity. Okay, so therefore, the more I calculate these details with precision from the particle physics, okay, I can extract more precise observable predictions. Okay, for the case of the n modulus, we calculated this number with these two parameters y, capital Y and m phi. Okay, now if I have a concrete form of the potential where I have control over all the higher dimensional operators, as string theorists claim, then I can calculate these numbers explicitly. Okay, so what we do, we take this so-called Kahler modular inflation where exactly the same scenario is actually happens. In that case, what happens is that this is an inflaton direction. Okay, so inflaton rolls down, and then there is a volume modulus, but at the end of inflation, the volume modulus is shifted from its inflationary minima. And at the end of inflation, the field rolls down here, but then volume modulus starts to oscillate along this direction. And the oscillations of this volume modulus along these directions produces exactly the matter-dominated epoch that I just talked, okay, that I'm talking about. Okay, so here I have a concrete example, okay, where I have the form of the potential is known and where I can calculate all the details explicitly. Now, some of the couplings has been calculated earlier, where the volume modulus decays later and the inflaton actually decays earlier. That's what you need because you want this inflaton to decay before the volume modulus decays. So the form of the potential was given, okay, by those group of people. So I'm skipping all the details here. Here, this is the tau n is one of the modulus which is actually shifted from its global minima far away. So this is exponential potential in the inflaton directions, and this is my volume modulus phi gamma. You can calculate in this case, the two parameters are important. Y, that I have assumed to be 0.1. So in this case, we have calculated what is the value of Y. You can do a perturbative calculations, analytic calculations, and you can show that the Y is the order of 0.1 to 1, which essentially validates some of the effective field theory argument that I have used earlier in the supergravity context. So this is an explicit calculations, and this verifies those arguments. Okay, and you can show that the other modulus, other than the volume modulus, are not shifted, okay, because masses are heavier during inflation. Now, in this case, you can also calculate the number of e-foldings, that is n modulus 1. Okay, and you can just, okay, so let me skip that. But the point is that the n modulus 1 can be calculated in terms of the microphysical parameter which defines the form of the potential. Similar way, you can calculate what is the number of e-folds produced by the oscillations of the modulus field. That also you can calculate, and you can show, you can see easily the dependence of the mass and Y parametrically goes exactly the same way that I have argued earlier. But the detail factors essentially changes. Okay. So as a benchmark example, so we just take, so these are the numbers that probably the initial model took to calculate the spectral index and tensor to scalar ratio. If you take the benchmark number, you just calculate now what is the value of n modulus, that is the number of e-folds generated from the oscillations of the inflaton field, which is order 1, which is insignificantly small, and then n modulus 2, which is 25.4. This is a large number. So therefore, now you calculate what is the NE. Here you have a better handle because now you have all the terms calculated, and you see this NE is shifted to 45. Okay? So then in that case, you calculate what is the value of NS, which is instead of 0.962, this number becomes 0.955. And in that case, T reheating becomes 10 to the 3 GeV. But what is the significance of these calculations? That is the following. The initial observations was at this particular point, black dot, by the authors who had proposed the model. Now with this more controlled the calculations of the post-inflationary history, the number of the spectral index becomes this number. And now this number is almost at the 2 sigma boundary line for the Planck data itself. Now you can imagine that once this is going to be the future contours. This is for the CMB stage 4 observations. That essentially shows that how it is crucial the observations of the NS and therefore the post-inflationary history of the universe. So in this talk, I just yesterday after John's talk, I realized in his model that he mentioned in the end very quickly, he also has exactly the similar sort of scenario, but the field is not modulus. In the model that if you look at it, this no-scale flipped SUSY model, he has a non-inflaton field, and at the end of inflaton, at the end of inflation, that field also decays and produces a lot of entropy. And n star essentially gets shifted from this n star standard minus 1/3 of this log delta, where delta is this so-called dilution factor. And they argue for the weak reheating cases, okay, when the reheating happens for a long time, then the spectral index predictions is changed substantially. So it's the same setup that I also discussed, but here also the field is just different, that's all. So therefore the coupling for this field is different than the coupling for the modulus that I discussed, but the picture remains the same. Yes. Yes. That's correct. That's correct. For strong reheating, the effect, because you quickly decay. So therefore there is no further changes. That's correct. So the crucial point is that it is important to understand the post-inflationary history is crucial to understand. So that's the kind of point I'm trying to make always. So let me come to the conclusion. So modulus dominated cosmology is a generic feature of string or supergravity motivated scenario. In this case, the crucial point is the number of E-folds, that n inflation changes from the standard number 55 by this factor, where y is the initial amplitude and mass, m phi is the mass of the modulus in the post-inflationary vacua. This is crucial because the NS sensitivity is going to go to the 10 to the minus 3 in future observations. This can be used also as a probe to what is happening in the post-inflation coupling with the modulus field to the other fields. So this same constraint can be interpreted as an independent constraint on the modulus mass derived using the CMB precision data. But this is definitely given an inflation model. So I talked about that for n greater than 45, the constraint is always stronger than the BBN bound. In the end, I just briefly mentioned the explicit calculations for the Kahler modular inflation. So with that, I thank you.
Can the moduli field act as a dark matter candidate or as a source for neutrino mass?
Yes. So for this sort of scenario, in the end, this moduli field decays and produces dark matter. And in that cases, the productions of the dark matter happens non-thermally, and that phenomenology people have worked out in details. I mean, because it's a late decay of the productions of the dark matter. So it may not be the standard thermal productions of the dark matter, because the temperature of the universe in the decay of the modulus can be very low also. So it may not be like, it may decay less than GeV temperature in principle. And that phenomenology for the productions of the dark matter, productions of the baryon asymmetry, has to be worked out independently, and people have worked a lot. For example, Affleck-Dine baryogenesis to produce the baryon number and so on and so forth.
The gravitational mass and your moduli wave or mass, because your moduli is breaking SUSY. So your soft breaking spectrum.
This I cannot say, because I need a more concrete model to.
Well, you have a model.
This for the scalar modular inflation.
Yeah.
Oh, scalar modular inflation, gravitational mass is very high.
So all your SUSY spectrum would be very high.
Yes. Yeah. But yes, that's correct.
So
scalar modular inflation, yes.
But does it the gravitational mass, does it depend upon the moduli wave or the moduli mass?
Okay.
I thought it depended upon the moduli wave. So if your moduli becomes 0, then your SUSY is restored.
Yes. So if the wave of the modulus at the end of inflation,
yeah,
is the same as the during inflation, then obviously it's completely.
No. During inflation you had M Planck, and at end of inflation it is 0.
Yes.
So does the SUSY get restored at the end of inflation?
If there is a term like M3 half square, something like that, that it can give you. Like,
so E to the K, that number, is it, what does it become when phi is 0?
No. So, yes. So what questions that you're asking?
So I'm asking what happens to the SUSY breaking parameter, that is the M3 half.
For example, the first part of my talk, okay. Actually, I cannot say, because because discussion is independent of that. Because discussions depends only on these two parameters, y and M3, y and M phi, nothing else. But for a concrete model, you have to calculate the spectrum explicitly. And as far as I remember, for the scalar model inflation, the spectrum is that M3 half is quite high, the gravitational mass.
Yeah, I think that your general point is very important and is well taken. I just wanted to repeat again what I said during your talk, that in this recent paper that we made, we actually looked at this quite carefully. We looked at behavior because we got a whole shitload of scalar fields, and we analyzed quite carefully what happened to those scalar fields.
Yes.
But I certainly agree that in general, this is something that people need to think about.
Yes, I completely agree with the fact, because I also read the paper yesterday. In the strong reheating, that means you actually reheat very quickly. Then there is no dilution, and therefore the effects almost, I would say the change is almost negligible. But if the reheating is weak, that means just decay longer later, then the effects is substantial. Yes, that's correct.